Okay, hello everyone. Today we're going to see probably our most important result in this whole course, but it will build upon all of the results that we had until this point, so it's not going to be too much of a theoretical hurdle. And then after the end of this session, I'm also going to talk again about the homeworks and give you more tips. So let's start with where we left off in the previous session. So we talked about translating LTL formulas into non-deterministic Boole automata. We said that for every LTL formula, there is some non-deterministic Boole automaton. I'm calling it B here, such that the language of the automaton is exactly the set of words that the set of traces that satisfy that LTL formula. Also, we talked about the complexity of the algorithm that we had for translating from LTL to NBW, and we said that the runtime was exponential, and also the size of the output NBW was also exponential in terms of the length of the original formula. Okay, so first of all, you remember where this exponential came from? Why it was exponential? So, right, yes. So we had these elementary sets, and our elementary sets were sets of sub-formulas, and because we could take any subset of sub-formulas in the worst case, it becomes exponential. Okay, now the algorithm that we saw previously is actually due to Wolper and Vardy. And we saw some examples of it in the previous session. For example, we saw that if our formula is this, next not P, it creates an NBW which has 4 states and 8 transitions. And the NBW gets actually much more complicated if you have until. So even if you had a formula of links 3, something like A until B, in the previous session, we saw that it leads to a Boole automaton with 5 states and 20 transitions. So here's a very simple question. Are these optimal, or can we have smaller automaton?
It seems they're optimal.
So for this specific formula, can you come up with anything that has less than 4 states? They're actually not optimal. So what do you think? How many states do we need for next not P? For example, can we do it with just 3 states instead of 4? No, actually, yes. So we can have an automaton like this, right? So when I'm saying next not P, I'm saying basically forget about whatever comes in the in place 0 in index 0 of the trace, and only check index 1 and make sure that you have not P there. So this is what this automaton does. It just has a transition that basically skips the first letter, and then in the second letter at index 1, it checks whether we have not P. So the construction that we had in the previous session is not optimal, at least not for this specific formula. How about A until B? Can we have a non-deterministic Boole automaton with less than 5 states that models this formula? Well, again, yes. And the basic idea is that when you have A until B, what you're saying is that in some finite prefix, I have A, and then I can end this finite prefix with B and go somewhere else. So you can have an automaton like this. It can stay here for finitely many steps as long as it reads A. And then when it reads B, it can go here and then it accepts. Okay. So even though we had an algorithm that could basically turn any LTL formula to a non-deterministic Bookey automaton, the algorithm is not optimal. So the question that comes to mind is, can we do better? Can we do better than exponential? And this is actually a question that we're going to ask many times in this session. So for many different problems, we're going to keep asking, can we do better or not? So there are actually many tools that do this kind of translation. They take an LTL formula and give you either a non-deterministic Bookey automaton, or in some cases, deterministic parity or Rabin automata. And they all have some sorts of heuristics in them. So for example, if you give this formula to one of these tools, it is very likely that you get an optimal NBW. But the question that I really want to focus on is, suppose that I have a magic way of computing the optimal MBW. For any given formula, I have a black box that I just give the formula to this black box and it gives me the MBW with the smallest number of states. Would it be better than exponential? Or do we still need the exponential blow up anyway?
So what is the difference? Is it only about this performance or something like that?
Yes, so well, when we're talking about exponential, for example, the algorithm that we saw takes 2 to the power of number of, 2 to the power of size of phi. So we might have an exponential algorithm that takes 1.1 to the power of size of phi, and that would be much better. But the real question is, can we do even better? Can we do better than exponential? So do you think we can do polynomial? So would that be possible? Okay. So actually, we cannot do better than exponential, and I'm going to give you a very short proof of this, not with all of the details, but you can fill in the details. So what I want to prove is that the exponential blow-up when you are translating an LTL formula to a non-deterministic Bookey automaton is unavoidable. So in order to do this, when I'm saying it's unavoidable, I have to say that, again, assume that I have a black box that gives me the optimal automaton, right? So I have to take some formula and I have to show that the optimal automaton for this formula will have exponentially many states. And actually, I have to have infinitely many of these, so I exactly do that. So let's say that the set of atomic propositions that I have is just a singleton. So I have just one atomic proposition P. Now I consider this formula, which I call phi n. So for every n, I get, of course, a different formula. What happened to that? Okay. So for every n, I create a formula phi n, and this is the formula that I have. And this I and n plus I that I'm writing here, it just means that I have the next operator n plus I times. Okay, so what is this formula saying? It's saying that for every I from 0 to n minus I, if you look at the index I of your trace, and if you look at index n plus I of your trace, they are equal. Basically, P holds in index I, if and only if P holds in index n plus I. Okay? So if I want to write some of these examples, so in case of phi 1, I have P if and only if next P. In case of phi 2, I have P if and only if after 2 steps P, and also next P if and only if after 3 steps P. And you can just create all of them in the same way. So basically what phi n is saying is that the first n letters in your trace should be equal to the second n letters in your trace. Okay? So which traces satisfy phi n? Exactly these things that I said. So the traces that satisfy phi n are all those traces sigma. such that the first n letters, sigma from 0 to n minus 1, is equal to sigma from n to 2n minus 1. So the second n letters. Okay, so the first question that comes to mind is, what is the length of this formula? Because I'm writing it in this shorthand format here, but in reality, the formula is this, right? So what is the length of my formula? We don't need to really compute it exactly. So do you agree that the length of the formula is polynomial in n? Why? Right. So we have at most n of these conjuncts, and each one of these conjuncts has what, a length of 2n plus 2 or something at most, right? And this is of course syntactic sugar, so you can rewrite it. So overall, the length of this formula is polynomial in n. Okay. So now what I want to claim is this. Even though the length of this formula is polynomial in n, the smallest non-deterministic Buki automaton that accepts this formula should have at least 2 to the power of n different states. Okay. So what is the intuition? Basically, what phi n says is that the first n letters should be equal to the next n letters, right? And then it doesn't really care about what happens in the rest of the trace that it's reading. So even though it reads an infinite trace, it only cares about the first 2 n indices. Okay, but how many different possibilities are there for the first n indices? Because I have one atomic proposition P can hold or not hold at each one of these indices. And this gives me 2 to the power of n different cases. Now, consider these 2 to the power of n different cases. The strategy that I'm going to use is very much like pumping lemma in normal automata, in finite automata. So what I claim is that if you write a list of all these 2 to the power of n different possibilities for the first n letters, and if you have an automaton that accepts this formula, then this automaton should go to different states in each one of those cases. Why? Because, well, it basically needs some sort of memory, right? It has to memorize what happened in the first n steps so that it can check that in the next n steps, the same thing is happening. So it has to be able to basically distinguish between any 2 different prefixes of length n. So any 2 different prefixes of length n should lead our non-deterministic Buki automaton to different states. Okay, so I will need at least 2 to the power of n different states in my non-deterministic Buki automaton. So what did this show exactly? So the size of the formula, the length of the formula was polynomial in n, but the minimum possible size for the Buki automaton was exponential in n. So the minimum possible size for the Buki automaton is exponential in the size of the formula. Okay, so we cannot do better than exponential. Okay, this is actually the last thing that I wanted to say about the translation between LTL and NBW. And what I'm going to talk about in the rest of this session is what we call LTL model checking. This is the most central problem that we're going to talk about. So we already know how to specify the properties that we want our systems to have. So any LTL formula can be seen as some sort of property that you want your software system or your cyber physical system, whatever system that you are verifying to have. And we also need to have a model of the system itself, right? And this is what we're going to use as modeling our systems. We're going to use Kripke structures. So let's say that again, we have our set P of atomic propositions. A Kripke structure over P is basically just a graph. So VE, these are the vertices and edges, together with a specific set of initial vertices. So V0 subset of V are our initial vertices. And also with this condition that there should be at least one edge going out of every vertex. So every vertex has at least one outgoing edge. So you can think of a Kripke structure as a transition system, basically. These are the different states of your system, and you can transition between them. And because we don't want to have finite paths, we are always saying that each vertex has at least one outgoing edge. This is similar to the case of games. But what's a little bit different with Kripke structures is that there is also a function L that assigns a set of atomic propositions to every state. And we call this set the label of that state. So for example, the label of S1 is P and Q. The label of S2 is just Q. The idea is that this models some software system or a program. And in this state, the atomic propositions P and Q hold. In this state, only Q holds. In this one, only P holds. Right? Okay. So this is a very simple modeling of how programs work and how systems work. We have a transition system, and we also have a labeling function that tells us which atomic propositions hold at every state of the program. Okay. So based on this, and by the way, I took this from Wikipedia. I was too lazy to draw one myself. So based on this, I can define two different notions. One is something that we have already seen, which is called a trace, and the other one is a run. So let's start with the run. So a run or an execution of this Kripke system is just an infinite path in this Kripke system that starts at one of the initial vertices. So in this case, I have only this initial vertex. So any infinite path that starts at S1 is a run or an execution of this system. So here's, for example, one of the possible runs. You can start at S1, go to S2, back to S1, back to S2, and then go to S3 and remain there forever. Now, so this is what we call a path, what we call a run or an execution. But then we also have the notion of trace. And a trace is basically the sequence of labels that you see during a run. So for example, the trace corresponding to this run would be this, because at S1, we have P and Q. So the run starts with S1, the trace starts with PQ. Then the run goes to S2, the trace will have only Q. The run goes back to S1, we have P and Q. Goes to S2, we have Q. Then the trace goes to S3 and remains there forever, so we have P forever. So a run or an execution is basically a sequence of states or a sequence of vertices in our Kripke structure. But a trace is a sequence of labels. A trace is a sequence of subsets of atomic propositions. And well, of course, you're very familiar with traces because that's what we've been studying for the past few sessions. So what's interesting for us? What's interesting for us is the problem of LTL model checking. And the LTL model checking problem asks this. So suppose that you are given some Kripke structure K and also some LTL formula phi in your input. You should decide whether all traces of K satisfy phi. So the question is it true that for every trace tau of K, tau satisfies phi? Or in other words, is it true that the set of traces of K is a subset of the traces that satisfy phi, or the meaning of phi? So the way we really think about this is that phi gives us the specification. Phi tells us what condition should be held in order for the program to be considered correct. And the Kripke structure K gives us all the possible runs of the program and all the possible traces. So the program is correct if all the traces satisfy our formula phi. Okay. And the problem of LTL model checking is basically to figure out whether this program is correct, whether all the traces satisfy phi. Okay. And in this session, we're going to mostly take an automata approach to this problem, because in the previous sessions, we already saw how you can translate the formula phi to a non-deterministic Buki automaton, right? So this was what we just talked about. So for the formula phi, there is a non-deterministic Buki automaton. I'm going to call it automaton of phi that accepts exactly the set of traces that satisfy phi. Now, the idea is that if we can somehow construct another non-deterministic Buki automaton that models this set, that accepts this set, then what we have to figure out is whether the language of that automaton is a subset of the language of this automaton, right? So if I can somehow construct another non-deterministic Buki automaton, and let's call it AK, automaton of our Kripke structure. And if I can do it in a way that it accepts exactly the set traces of K, so it accepts an infinite trace, if and only if there is a run in K such that this trace corresponds to that run. Okay, so if I can construct such a non-deterministic Buki automaton, then the only problem that I have left is to figure out whether the language of this automaton is a subset of the language of this automaton. Okay. So as you see, we went from kind of a logical world into a more automata-based world. So there are two problems here. The first problem is, how do we construct this non-deterministic Buki automaton AK? And the second problem is, how can we decide whether the language of one automaton is a subset of the language of the other?
Why do we need to construct the
So if you want to do your model checking on the Kripke structure, the problem is that the set of traces is infinite, right?
Yes.
So there are actually ways, there is something called game-based model checking that doesn't translate this to an automaton and only translates the formula to an automaton. But I think that becomes more complicated than what we're doing here, because what we're doing here gives us a little bit of uniformity in the sense that instead of having an LTL formula and a Kripke structure, we just have two objects of the same type. They're both automaton.
So it's about just the computation, right?
Yes, and also at the end, the runtime would also be better if we do this. So we will see. Okay. So I have to now solve two problems. The first problem is, how do I create an automaton that accepts the traces of my Kripke structure? This is actually quite easy, and we're going to see this first. And the second problem is, I have two non-deterministic Buki automata. How do I decide whether the language of one of them is contained in the language of the other? Okay, so let's construct this non-deterministic Buki automaton AK. So I have a Kripke structure. I have a set of vertices, a set of initial vertices, a set of edges, and I also have labels on my vertices. Okay, so I want to construct a non-deterministic Buki automaton that accepts the traces of my Kripke structure. So the first question is, what is the alphabet that we're going to use in our non-deterministic Buki automata? Well, we want the language to be the set of traces of K. And in traces of K, the alphabet is what? It's 2 to the power of P. It's all the subsets of atomic propositions. So the alphabet in our automaton should also be the same. It's 2 to the power. Now, actually, the construction is super easy. What we do is that we just take the states of our Kripke structure as the states of our automaton. And we also take the initial states of our Kripke structure as the initial states of our automaton. The only difference is that whenever I have an edge going out of a vertex, so let's say I have this edge going out of S1, in my automata, the edges are going to be labeled, right? But in my Kripke structure, the vertices were labeled. So I just give the label of every vertex to all of the edges that go out of that vertex. So this is basically a fancy way of saying the same thing. So I'll just remove this label from here and put it here instead. I remove this label Q from here and put Q here and here. And I remove the label P here and put it here. So let me actually do that. So Q, this is Q. It's really hard to do this with the mouse. Okay. Now, why does this make sense? Because, well, I was seeing P and Q in this vertex in my original Kripke structure. Now, instead of saying that I see them there, I say I see them as soon as I go out of this vertex. So this doesn't change much. And what is the accepting set? So the set of vertices that we want to see infinitely many times. Well, we want to accept all traces of K. And traces of K are basically the infinite paths. So all I want is for my path to be infinite. So I just let T be the set of all vertices. So this very simple thing translates a Kripke structure to a non-deterministic Buki automaton that accepts its traces. Okay. Any questions?
They don't differ because I'm just talking about the previous question I asked. What is the difference between just extracting the non-deterministic?
Yeah, the difference is very small. The difference is only in what we label, but the thing is we will then do some operations on these. We will do some automata operations on this. So we might get some automaton that cannot be translated back to a Kripke structure. So
but we have the assumption that any vertex in Kripke has the outgoing edge.
Yes. Yeah, they have that assumption. Okay, so now the second problem. I have two different automata. I have automaton of my Kripke structure and automaton of my LTL formula. And I want to figure out whether the language of this one is a subset of the language of that one. Okay. So let's do a first attempt and let's just try to write what this means. Like, let's just write equivalent formulations of this. So the language of AK is a subset of the language of A phi if and only if this one does not intersect the complement of this one, right? So this is just set theory. A is a subset of B if and only if A does not have anything in common with the complement of B. So I just take this and rewrite it like this. This is basic set theory. Okay. So now here I have complementation. And several sessions ago, we actually saw how we can complement non-deterministic Buki automata, right? So I can create another automaton, let's call it B of phi, which is the complement of this. Okay. Now I have an automaton for this part, but I also need to take intersection. So let's see be an automaton that accepts the intersection of this and this. Okay. Now, what was the question that we had? The question that we had was whether this thing is empty. So our question is basically emptiness checking on this automaton C. Does C accept something or does it accept nothing? We just want to do emptiness checking. Okay. So every step of this gives us a kind of new problem. Some of them we have already seen. So the first problem is, how do you compute the complement? And we already had a whole session on this, which was about Bookie's way of complementing non-deterministic Bookie automata. Another question is, how do we compute the intersection? This is homework 3, but since no one has got it yet, I'm going to show you now how you can do this. It's very similar to homework 3, and we'll do this. And then finally, our last question is, how do you check emptiness? So you have a non-deterministic Bookie automaton C. How do you check that the language of C is empty? We have seen this before as well. So the basic idea was that if you have a non-deterministic Bookie automaton and you want to check its emptiness, you can think of it as a game, as a Bookie game, where all the vertices belong to player 1, and you can just solve that game. So that it's a single player Bookie game. Or another way of looking at it was that, well, the language of C is non-empty. If starting from some initial vertex, you can reach a cycle that includes an accepting state. And we showed that actually you can do this in linear time. You have to just look into the strongly connected components of C. So this is kind of easy. This is what we're going to do now. And this one was actually quite hard. As we saw, the complementation wasn't really a trivial problem at all. Okay. So let's do the intersection. But before doing that, let me show you another problem that we had in the 2 sessions ago, which was very similar to this. So the problem that we solved in 2 sessions ago was that, let's say we have a generalized non-deterministic Bookie automaton. So we had several different sets of states that we had to visit infinitely many times. And we wanted to construct a non-deterministic Bookie automaton. And the technique there was just to take several copies of the original automaton and go from one copy to the next copy whenever you see a target state, right? Now, here, what do we have? We have 2 different automata. We have the automaton A, and I'm putting subscript A for everything here. And we have the automaton B. And we want to compute another automaton C that accepts their intersection. But okay, what is intersection? Well, A accepts all the executions that visit T of A infinitely many times. B accepts everything that visits T of B infinitely many times, right? So we can have a similar construction, except that instead of K sets, we have only 2 sets. We have only TA and TB. But there's also some other complication here. And the complication is that the set of states is also different. So I cannot just assume that the set of states of A are equal to the set of states of B. What can I do? Well, I can just get the product automaton and basically simulate both A and B at the same time. Okay? So we need 2 different ideas at the same time. One idea is that I'm taking the product automaton of A and B. And the other idea is this idea that I take 2 copies, and every time I see a target in A, I go to copy 2, and every time I see a target in B, I go back to copy 1. So this is how we do it basically. This was too hard to draw, but so the set of states are basically the cross product of the set of states of automaton A and automaton B, but we also take 2 copies of it. The initial states are initial states of A times initial states of B, but we are initially in copy 1. Then whenever we want to do a transition, we do the transition we basically simulate the transition in both automata at the same time. So if I'm at the state QA, QB in copy 1, and if I read the letter A, I apply the transition of the first automaton to the first part. I apply the transition function of the second automaton to the second part. And I stay in the same copy if I'm not in a target state. And I go to the other copy if I am in a target state. And these are just similar. these are just the same as this, except that whenever we get to targets of B, we go back to copy 1. Okay, and what is our target set? What is it that we want to visit infinitely many times? Well, I can just say that let's look at our first copy. And let's say that I want to see the targets of A, and I don't care what I see about B, but I want to see the target sets of A in the first copy infinitely many times. Why is this sufficient? Because whenever I see a target of my automaton A in the first copy, I will have to go to the second copy. And then I can only come back if I see a target of the automaton B. So if I see a target of automaton A in the first copy infinitely many times, this means that I've also seen a target of automaton B in the second copy infinitely many times. So this is how we compute intersections of two non-deterministic Boole automata. And the thing that I really want you to note here is that this whole construction can be done in polynomial time. So with respect to the sizes of the initial automata A and B. So it's actually order n squared, right? So not only it's polynomial, it's even quadratic, which is much better. So let's come back to our overall view of how things are. So this was the main problem that we wanted to solve. We wanted to see whether the language of AK is a subset of the language of A phi. And we did all these steps. Now I want to see what the overall time complexity is. So first, we are computing this complement, right? What was the complexity of complementing non-deterministic Boole automata? Well, the algorithm that we saw, which was due to Boole, did this in doubly exponential time. So 2 to the power of 2 to the power of size of the original automata. Okay. Now, what is the complexity of computing intersection? We just saw that it's polynomial. And what is the complexity of emptiness checking? Well, we saw that we can do it in linear time. But there's also something else here. So I'm starting this assuming that I have these two automata. I have an automaton that basically models my Kripke structure, and I have another automaton that models my formula phi, right? We saw that finding this automaton is easy, but finding this automaton was the subject of the previous session, and it actually took exponential time, right? So before all of these steps begin, I have to spend exponential time in terms of phi just to compute this automaton A phi. Okay, so let's put all of this together. So the size of the automaton for Kripke K is actually equal to the size of K, but let's say it's polynomial in the size of K. The size of the automaton for our LTL formula is exponential in the length of our LTL formula. Then we are complementing this automaton, which takes doubly exponential time. And then we are taking the intersection, which is polynomial. And finally, we are doing emptiness checking, which is linear time. So putting all of these together, our algorithm has polynomial runtime in K. Actually, it's easy to show it has linear runtime in K in size of the Kripke structure, but it has triply exponential runtime in the size of our formula. So if the size of the formula is, let's say, T, our algorithm is something like 2 to the power of 2 to the power of 2 to the power of T. Okay, so our dependence on K is great. Like it's polynomial, actually it's linear even. So there's nothing to improve here. This is great. But can we do better here? Because if it's triply exponential, it means that you basically cannot check any formulas, even if you have a simple formula that is like 5 letters. Okay. Any ideas for how we can do better than this? So Which one of the steps can be made better? The first step was that we took our formula and turned it into a non-deterministic Bookey automaton. At the beginning of this session, I just showed you that you cannot do better than exponential there. So there is nothing to improve in creating this A phi. This one was created in linear time. So we don't have anything to improve here either, right? And then the intersection and the emptiness checking also took polynomial time. So as far as we are concerned with removing the tower of exponentials, these are also not really interesting. What's really interesting is how we can get rid of the doubly exponential complementation. Right, so when I'm computing the complement of this non-deterministic Bookey automaton A phi, and I'm calling it B phi, why am I spending doubly exponential time? And can I do better using the tools that we've seen until this point? Sorry. So if you remember when I told you about the algorithm of Bookey for complementation, I told you that it's just, its use case is just theoretical. It just shows that you can do the complementation, but it's not really meant to be used in any applications. So we've already seen a case where complementation was easy. What was that case? If our automaton was deterministic, then computing the complement was easy. And this actually held for any type of deterministic automaton. So if you had, for example, a deterministic Bookey automaton, you could easily complement it. But also if you have, let's say, a deterministic parity automaton, you can just increase all the priorities by one, and that complements the automaton, right? So complementing deterministic automata is much easier. But several sessions back, we also saw an algorithm for determinizing the automata. We had an algorithm that took a non-deterministic Bookey automaton and turned it into a deterministic Rabin automaton or a deterministic parity automaton. These were the algorithms of Safra and Peterman. So let's use those. So yeah, let's basically be a bit smarter in how we do complementation. So instead of complementing A of phi directly using Bookey's algorithm, we first determinize it. So let's say that I determinize it either using Safra's algorithm to a deterministic Rabin automaton, or using Peterman's algorithm to a deterministic parity automaton. And for our use cases, it doesn't really matter which one you choose. So let's call this deterministic automaton A prime of phi. And of course, the whole point of determinization was to not change the language while getting rid of non-determinism. So the language of A of phi is the same as the language of A prime of phi. Okay, now instead of complementing A of phi, complement A prime of phi and call that P of phi. Here. Okay, so what do we gain by this? Basically, previously we were spending doubly exponential time here, but now we are only spending exponential time to determinize, and then we are complementing it in polynomial time because complementing deterministic automaton was easy. Okay. So again, we can go through our algorithm and its complexity. So computing this automaton was easy in linear time. Computing this automaton took exponential time, and we showed we can't do it better. Computing the complement is now done in exponential time. We showed how we can do intersection and emptiness checking in polynomial time. So putting all of these things together, what is our runtime now? It's linear in the size of the Kripke structure, in the size of our system, but it's doubly exponential in the size of the formula. Why doubly exponential? Because I have an exponential here going from the formula to its non-deterministic Bookey automaton. And then I have another exponential here when I'm determinizing it. Okay. This is much better. Using this, you can actually now solve some toy problems probably. And doubly exponential is definitely much better than triply exponential. But can we do even better than this? Can we even reduce this below doubly exponential? There's actually a very nice trick for doing this. And let's see if you can find it. So again, the part that we want to really optimize is this computation of the complement, right? And right now we are spending exponential time there. Yes, exactly. So the thing that is actually important here is that when you're talking about a phi, it's not just any non-deterministic Buki automaton. It's the non-deterministic Buki automaton that corresponds to the formula phi. So what is the complement of this automaton? It's the non-deterministic Buki automaton that corresponds to the formula negation of phi. Right? So instead of complementing on the automaton, let's do the complementation on the formula. Let's say that I first create the formula negation of phi, and then directly say that, okay, B phi is the non-deterministic Buki automaton that models this, that corresponds to negation of phi. So in just by paying only one exponential price for going from LTL to non-deterministic Buki, I directly got this automaton B instead of getting the automaton A. Okay, so I do this exponential thing, and then intersection was done in polynomial time, emptiness checking was done in linear time. So I don't know why these things are white. So the whole thing is much faster now, right? So what is my complexity now? Yes. So it's polynomial in the size of the Kripke structure, actually linear in the size of the Kripke structure, but it is exponential in size of phi. Okay, great. So what does this mean? This means that as long as the formula that you write is relatively short, you can actually check it over systems that are quite large, because your runtime dependence is only exponential in the size of the formula. And most of the time, the formula is really short. So what are some formulas that are actually used in verification? We can have a formula, for example, for reachability. The formula for reachability was just eventually that state that we want to reach, right? Or we can have the formula for Buki, which was always eventually, and then that atomic proposition that we want. So as you see, it's very rare that the formula gets long. Usually the formula is quite short. So this is actually a very good complexity, and it works in many cases. Okay. Now, can we do even better? I said, this is the theme of this whole session. Like, can we do better? We have one problem and we just want to keep doing better and better. Yeah, but then this probably wouldn't work for all formulas, right? Actually, I'm going to say that we cannot do much better, probably. And so before we do that, let's just do a summary of what we saw. We saw that if we have a Kripke structure K and an LTL formula phi, the model checking problem can be solved in time polynomial in K and exponential in phi. And what did we mean by the model checking problem? We meant the problem of deciding whether all traces of K satisfy phi or not. Okay. So let's talk about how we can do better and whether we can do better. So first of all, we certainly cannot do any better if we want to translate our formula to a non-deterministic Cookie automata. This was the first thing I showed in this session. You need exponential time for that. So the question that comes to mind is, okay, what if I can find some other type of model checking algorithm, something that doesn't even depend on automata? Then would it be possible that somehow I can get better? And actually the answer is probably not. And this is because of the complexity of the problem. This problem is p-space hard. And the complexity of LTL model checking is actually the topic of the next session. But let me just say a few words about what it means that the problem is p-space hard. So p-space is the set of all problems that can be solved using a polynomial amount of space. So consider a Turing machine, and let's say we don't care about how much time it takes. We only care about how much tape it uses, how many memory slots it uses. If the memory usage is polynomial, then this is a p-space algorithm. And a problem is a p-space problem if it has a p-space algorithm. So when we say that this problem is p-space hard, it means that it's harder than every other problem in p-space, right? And p-space is actually much more general, well, kind of more general than NP. So you can't really hope to solve it in less than exponential time. The fact that we have p-space hardness means that we don't really have a good hope, but also we don't have a proof. So it might be possible that someday someone solves it in less than exponential time, but then everything in p-space will be solved. Okay. So this is what we're going to cover in the next session. This was all I wanted to teach in this session. So I'm going to stop the recording and then we can talk about other things. So let's stop this recording.